Professor Ian Walmsley, talking about scalable photonic quantum networks.
Thanks, Mike. Yeah. So does that mean we have a home team advantage? Is that?
Yes.
Yeah.
Can't do anything to win.
We got the Mexican wave there. Great. So, well, good morning and welcome to Oxford. Those of you who are not local. I'm going to talk a bit about some elements of work in the group here towards building photonic quantum networks. And by that we mean obvious things. It's going to be a network that uses light as the carrier and information processor. That it's going to be quantum in the sense that what we're aiming towards is something, a network of a scale that we cannot simulate its behavior efficiently on a classical computer. There's a subtitle which you'll understand as we get to the end of the talk to do with how you build these things in the real world, if you like. It's not. It's a fantasy world. Real talk. These are the group of people who have contributed to the work that I'm mainly talking about today. Some is not as up to date as it might be. Josh Nunn has been leading on the quantum memories part of it, and some of the work we've done in collaboration with these guys at the bottom. Okay. Oh, let's see if this works. Yes, as you well understand, all quantum mechanics is about contextuality. Now, is this going to actually work? Do you have volume here? Let's bob around.
Yeah.
Yeah.
It should be, I think, if it's connected.
So,
I've never used this.
Alright, let's give it a shot, see what happens. Whoa, no, that's not what I wanted. No, that's not what I wanted.
Electric field, is it a useful fiction for representing the movements of information, or is it a chimera?
Don't know.
Another beer?
Yeah. There you go. Now, that's the deep philosophical discussions we have over in Clarendon, and I should tell you they must be deep because those guys both have faculty positions now, one in Bath and one in Ottawa. So there you go. So be careful. Right. So some background context. One thinks about a quantum network as a way to distribute quantum correlations across many different nodes. And it may be as part of a computing network, it may be a communications network, there may be part of a simulation network, if you like, but there are many different possibilities. And what has been known for a number of years is that a key protocol to enable one to do such distribution is the so-called quantum repeater. And what one does there is to break up the network into smaller sections so that one can distribute entanglement effectively across those sections. The main problem being, of course, that photon loss is the thing that mitigates against getting anything quantum mechanical distributed over long distances otherwise. What that implies is that one makes use of quantum operations to effectively link up the different parts of this network, and that in the DLCZ repeater protocol, at least, that these quantum operations are probabilistic. And a key element of that protocol, and a key element of scalability in all situations where one uses probabilistic operations, is that you need to use a repeat until success strategy. You wait until the operation delivers the outcome you require, and you store that. And if you repeat that many times, you end up building something that's deterministic. And that implies that you need quantum memories. Now, what are the sort of parameters that you need to worry about for quantum memories? Well, there's two, there are many, but there are two that are important at the moment. The first of those is a fairly obvious one, that the physical scale of the network must be commensurate with the lifetime of the memory. If you want a global scale network, then you're going to have seconds, milliseconds to seconds of lifetime in your memory. The second one is not quite so obvious, but I will illustrate it, and I hope to convince you that it is an important parameter, and that is the time bandwidth product. And by that, I mean the ratio of the lifetime of the memory to the time scale of operations that you can perform on that memory. So if you have a lifetime that is a microsecond, and yet you have an operation time scale that's a nanosecond, then you've got a time bandwidth product of 1,000. So even though the absolute lifetime is not useful for a global scale network, there are still many operations that you can perform during the lifetime. Here's another example of, or a specific example, if you like, of probabilistic operations relating to entanglement distribution. It's the case of continuous variable entanglement and the ability to distill entanglement over networks. So one starts with a so-called Gaussian entangled state, say a two-mode squeeze state, and that may have entanglement of a certain magnitude, certain quality. What is known is that in order to improve the quality of that entanglement, one needs to effect a non-Gaussian operation, and a typical sort of operation that one uses is photon subtraction. And the way that that works is illustrated in this little box here, or this little circle here. You put a small beam splitter or a low reflectivity beam splitter in the beam, and then you direct a bit of the light onto a photodiode, which registers a single photon. And when you register that single photon, you know that you have subtracted one photon from the upper beam. But of course, it is probabilistic in the sense that each time you run this apparatus, you may or may not get a registration from that detector. However, if you do get a registration from that detector, then one can show by various means that the entanglement of that beam has been increased. And the reason is fairly straightforward, that the probability that you decrease the amplitude of the vacuum component of that beam, and you increase the other amplitudes progressively towards higher photon number, simply because it's more likely that if you subtract a photon, that would have come from a higher photon number component. Okay, so how do memories help in such a circumstance? Let me give a specific example here, that's the third example, which is how you build a deterministic n-photon source, if you like. So there are many ways in which you could conceive of doing that. You could have n single photon emitters in cavities and bring them all together. But the way I've illustrated here is a particularly simple and well understood way, which is you take a device, and that's illustrated by this box here, which generates photons 2 at a time. And there are many such devices. A parametric down converter is one, a four-wave mixing in a Kerr medium is another. Either way, you know that you're always generating these in pairs, so that if you take a detector here and that detector fires, then you have a heralding signal that tells you there's a photon over here. Of course, because it's a spontaneous process, that doesn't happen each time you run the apparatus. So again, it's a probabilistic outcome. But nonetheless, when this detector fires, what you do is turn on the control signals for this memory, and you store the heralding light in that memory. Well, you can build up your n-photon source by having n sources of this kind and n-1 memories. and then that repeat until success strategy allows you to wait until each of these is fired once, you store the outcome and then turn off that source, and eventually you fill up all these memories and you've got your n photon source ready to be popped out into your network. Because it's probabilistic, a key performance parameter or analysis might be sort of as illustrated in this graph here, where the vertical axis here is the waiting time. That's how long you have to wait to make sure that you have your n memories or n minus 1 memories filled up, plus this last source firing. So the number of sources that we're trying to synchronize is shown here along the bottom axis. Now, there are three bar graphs here, and the blue one is the case where you have no memories at all. So you simply want to run these sources in parallel and ask, how long do I have to wait before all n of them fire at once? And you can see that that is exponential in the number of photons that you want. And, well, that is the way it is. We often, at the moment, all experiments work that way. But you can immediately see why this becomes a bit of a problem. Here's where we are at the moment in terms of numbers of photons. About 8 photons is the current record. And you can see that you get sort of 8 photon events once every 10, 20, or 10 to 100 seconds. That's the kind of time frame you're looking at. Well, if you now want to get into a regime which some argue is not simulable classically, you need to be up here in the 10 to 12 region. And you can see that the problem with the current way of doing things is that you'll end up waiting 3 years or more for a single event. So that's clearly not a tenable sort of experiment. Now, what happens if you have memories is shown here in the red and the green boxes. And what you can immediately see in the red one is, again, an exponential scaling, but where the scaling constant is much more favorable. So that in principle you can get into this regime of 10 to 12 photons with events coming at a reasonable rate. The green case shows something where you're essentially now in a regime which is effectively scalable. And the difference between the red and the green curve is the memory efficiency. So that is the ability of the memory to both store and read out the state that you put into it. So a key message here is that using memories helps you. In principle, it can get you scalable if you have perfect memories, but even in the case where you don't, you can get into a regime where something we hope palpably new happens. The bullet point says the parameters that we used in this calculation, and a key point to note is that this assumes a memory with a time bandwidth product of 1,000. And in fact, that enters directly into the improvement rate. So if you have, effectively, it's the efficiency times the time bandwidth product to the power n, that is roughly the scaling. Okay, so that's to illustrate what it is. Let me tell you now what I'm going to tell you about in detail, which is some technical matters associated with building memories that you need to operate such a network. And the first message is going to be you can build photonic quantum memories that are robust, i.e. in the sense that you can build them in a laboratory without too much hassle. I know you guys are going to tell me that it is a lot of hassle. But it could be more hassle. And they're fast and simple. Fast in the sense that they have a high time bandwidth product. The second important thing, which I will illustrate by way of a calculation, is that quantum memories don't have to be perfect to be useful. And the particular thing I'll show you is a transformation of the scaling properties of a CV entanglement distillation network, which move it from the exponentially difficult regime into the merely polynomial. And then finally, an exploration of whether one can really begin to conceive of these things working in what you might call the ultimate of robustness configurations, that is, room temperature solids. So first steps in that direction. Okay, so a quantum memory, when we conceive of it in the context of an optical scheme, it is the connection then between static and flying qubits. So we have a quantum state of light, and we're going to map it into a quantum state of matter. And we'd like to do that in a way that the bandwidths are compatible both with the nonlinear optical sources that we can build and with the sort of communication speeds that we want on networks. And the archetype of this is illustrated here. We're going to have some material system which has a metastable configuration that stores the static qubit, if you like. And then we'll take the flying qubit in the form of a single photon, and we will couple those two together by means of a control field that we can turn on and off. So that's how we'll do the read in, and then sometime later we'll come with a second control pulse and we'll read out. So we'll have a write control pulse 1 and a read out control pulse 2. And that sort of concept for a quantum memory has been around for a decade or so. Fleischauer and Lukin first came up with it in 2002, and there have been many, many different versions of that up till now. Those have largely been based, well, they've all been based on things that are very cold. That's either been cold trapped atoms, either in a magneto-optical trap, an atomic gas, or single atoms trapped in cavities, or they have been in cold solids. And it's only in the past few years that people have conceived of ways to build these in warm matter. And so the one I will talk about now is the one that we've been working on, the Raman memory. And there's another scheme that uses warm atomic ensembles called gradient echo memories, which has been developed by Ben Buchler in Australia. I can talk about that later if people want to ask questions, but I won't illustrate very much the differences between Raman and Chern. Okay, so within each of these atoms, the sort of structure that one looks for is illustrated in this cartoon here, where there will be two metastable states, typically separated by some energy difference, and those will be the states where we store the internal qubit, and that we will address those two states, which are normally not coupled, by means of two optical dipole transitions. So this would be a ground electronic state, say, and this is an excited electronic state. We will have a control pulse here, shown in green, and the quantum light pulse coming in here, shown in blue, and that the logical 0 and 1 states we map onto the ground and excited states at this ground metastable level. And a key point for the Raman memory is that we have a very large detuning of those dipole resonances, and I'll explain why that's a useful feature later. Now we take each of these atoms and we just bung them into a gas cell, and then we have an atomic ensemble. And now, the main difference is that instead, what we have is a situation where the probability that the quantum light pulse is absorbed in any given atom is rather small, because the coupling is relatively weak. But if we put enough atoms into this cell, then the probability that the quantum light pulse is absorbed somewhere in that cell is actually very high. So effectively, this looks dark. It's a black cell. When the control pulse is on, if you like. But the trade-off is we don't know in which atom, say, a single photon has been absorbed. And so the qubit is now the collective internal excitation of the entire ensemble of atoms, rather than the simple internal state of one of the atoms. And there are certain useful features about that. And one of the useful features is simply this: you can store lots of photons. And therefore, if you're thinking about a way to build a memory where you've got many modes that you could store all together with many photons in there, this is a reasonable way to do it. If you have a single atom sitting in a cavity, of course, you're limited to one photon at a time. So here's the particular experiment that I will show you some details of. It is of the kind that I have just illustrated, where the specific atom is the cesium atom, and the optical dipole transition is between the ground S state and the excited P state, so the D1 line, except we're detuned by around 30 gigahertz from that D1 line. Now, what you see in the cartoon again is the pulse sequence. We have a right pulse that is the control signal coincident with the quantum lights we wish to store, and then sometime later we put in a read pulse. What comes out at this end is the residual, the control pulses, they're not absorbed at all, and some residual transmitted signal, and then the retrieved signal when the right pulse comes along, when the read pulse comes along. So what's the important feature here of the Raman memory? Well, we have large detuning, and that means that we're quite insensitive to inhomogeneous broadening. So we effectively use all of the atoms in the gas cell. And that's different from an EIT memory where one is tuned to a particular resonance and therefore uses one velocity class of atoms more than the others. Second, and most importantly, is that we have low noise. And the reason for that is that there is no real population in the excited state. So we don't get any fluorescence from light that's absorbed onto the D1 transition. And that arises from the detuning. So the signal's then absorbed into a virtual resonance, which is the 6s1/2 hyperfine levels F3 and F4. So those are the ground, the metastable states. And it's done by this virtual resonance through the D lines. Again, the fact that we have got large detuning means that the storage is broadband, because the absorption resonance bandwidth is determined by the bandwidth of the control pulse, rather than, say, the Rabi frequency of the control pulse. And second, because again we're strongly detuned, the, if you like, failure mode is transmission. That is any light which is not mapped into the memory state itself simply goes straight through and out the other side of the memory. So the memory behaves effectively as a beam splitter, a light matter beam splitter. You shine light on it, either some fraction of that light is stored, some fraction of the light goes through. And that ability to both store and process light simultaneously turns out to be a very pleasing feature, because you can build in light matter entanglement very easily. So how does this memory perform? Here's an example. So the vertical axis shows the transmission of light pulses through the memory, and the horizontal axis shows the time with respect to the right pulse. So the blue line shows the case of a weak coherent light pulse going into the memory when there's no control light on it at all. So you get 100% transmission, nothing is stored. When you turn on the control pulse, you see what happens is that you absorb some of the light, illustrated by this dashed red line here. So you absorb about 30% of the light. And then when you come along later on with your read pulse, you can pop out about half of the light that has been stored. So in this case, the overall efficiency is about 15%, readout of 50%, storage of 30%. Current performance is somewhat better than that, but I'll show you where we expect to be able to get to in a second. This inset here shows a blow-up of the readout of this memory, and you can see a key point that I'd like to make now, which is that this is a relatively short pulse. This is a nanosecond long. In fact, that's limited by our detector. So we believe, from measurements of the pulse itself using other means, that output is in fact about 200 picoseconds long. So we have a memory that's got a bandwidth of about 2 and a bit gigahertz. Okay, and the fidelity of the input and output pulses is around 80% or so. And we can show that by illustrating the interference between some of the transmitted light and some of the read out light later on, so you can see that they remain coherent. What limits that visibility? Well, there's some dispersion in the medium, and there is a stark shift that's associated with the change in modes between input and output by virtue of the fact that we have a relatively strong control field. Those are unitary operations that you can in principle undo. There are technical challenges to actually doing them, but we don't believe they're a fundamental limitation to memory performance. To show how the efficiency works, here's that same graph again, transmission versus time delay now versus read and write pulse energy. And you can see that as you crank up the read and write pulse energy, first of all, if you crank up the write pulse energy, you absorb more. If you crank up the read pulse energy, you read out more. And those are shown on the graphs over on the far right-hand side, where it's shown the efficiency versus the read and write pulse energy. The top two are illustrations of what we expect, illustrations of a model fit to the experimental data itself. And the bottom one shows, in the blue region, that's the experimental region, so they're the same lines as above. But to the right, in the white region, is where we project that this memory can operate to. And you can see in the optimal case, we can work this configuration up to about 70%. And the reason we can't go any higher has to do with mode matching for forward and backward readout, which is a technical detail that I won't get into. One can improve it by changing the configuration of the memory. How about the quantum properties of the memory? Well, we can look at that using quantum process tomography, so mapping an input quantum state to an output quantum state and looking at the Krauss decomposition in terms of this chi matrix, which specifies the quantum process associated with the memory. So we do that by looking at just one element here, chi 0, 0, and the closer that is to 1, the better the quality of the memory is. So here's the way in which we do that. We adopt a trick to make the memory into a two-mode memory by having two beams going into the same cell. And we configure those using a method developed by Andrew White's group in Queensland of using polarization multiplexing. We then adopt the method that Lvovsky developed for developing quantum process tomography by way of coherent states to illustrate the memory performance. And you can see here that we get a process purity of 99%. That's at a delay, a relatively short delay, but the process purity turns out to be quite good, even as the efficiency goes down. So the purity is maintained as the efficiency decreases at longer delays. I mentioned that the feature of these memories was that one had low noise, and if one wants to build a network, then noise is clearly a critical thing. So here's an illustration of what the noise level is. The green line shows the case when there is no control field, so that's just the signal going straight through. The blue line shows what the signal field looks like when we add the control field on. So you can see good absorption, good readout. And then the red line shows what happens if we turn the control field off, turn the signal field off, but still monitor the signal line. And you can see that there's some noise associated with the control field being present. And that noise is about a quarter photon per cycle. So that's not zero, but it is pretty low. And is it low enough? Well, here is a way to measure that, which is to use this scheme developed by Serge Moussard and Sandu Popescu to ask whether a memory operates beyond the classical limit in the sense that it preserves Bell inequality violation. If you do the measure and prepare, interrupt, resend, you find that maximum fidelity you can get from that classical scheme is 2/3. And if you adopt what our memory has, you can see that the performance figures I just showed you give us 70% greater than 2/3. So arguably, we're in the quantum regime. Let me illustrate now the case of this feature that the Raman memory acts as a beam splitter. So, as I illustrated earlier, we have the possibility to take a light mode and a matter mode and have them interact according to this very straightforward and simple beam splitter interaction, ending up with one of the modes stored and one of the modes transmitted. Importantly, that is a time mode selective beam splitter. That is, we can pick out a particular temporal mode from the input beam by changing the shape of the control pulse. So it's like a switchable beam splitter, if you like. We can now use that in the following way. You can imagine that we write something in, we write our signal pulse in, and then we come along with some sequence of read pulses. And by adjusting the amplitudes of these read pulses, we can effectively build an array of beam splitters. So here's an example of that. The cartoon at the top is the equivalent beam splitter sequence to what is shown down here, which are the memory read-in and read-out sequences. So here is the control sequence, a write pulse, followed by different patterns of read pulses. You can see here the write pulse occurs at time 0, the read pulses occur about a second later. And the red here shows what the light pulse, the quantum beam, in this case the weak coherent state again, looks like. And you can see that as you change the beam splitter sequence, the outputs look exactly as you would expect from cascading that pulse through the beam splitter sequence. And it remains coherent, which you can show using the tomographic multimode setup that I showed you earlier. So why is this helpful? Because these memories are great memories. I showed you that the overall efficiency is around 50%, and that we can adjust that downwards by changing the control pulse amplitude. Well, here's a reason why they're helpful. We go back to this case of entanglement distillation, as to how we prepare high-quality entangled states from low-quality entangled states. And I gave you the example of non-Gaussian operations on a two-mode squeeze state. So how do we distill entanglement in that way? Well, let me denote the output state from this operation. So that's the state sitting right here as a photon subtracted state, psi superscript I. If you take that, then there's a well-known scheme developed by Dan Brown and Jens Eisert and Martin Plenio from 2003, by which you can take many copies of that state psi I, and you can build up a single copy of state which has more entanglement. And that's shown right here. So here's two copies of that photon subtracted state. You mash them together at this beam splitter, and by mashing, I mean the following. You take the light here, you take the light here, you put it on the beam splitter, and then you look for the situation where no light comes out of that output port there. You do that on both sides, and you find the state here, psi I plus 1, the first iteration, has a higher degree of entanglement. So that is a situation where you iterate this map to build up entanglement, and it contains your archetypal probabilistic quantum operation right here. So it immediately suggests itself as a place in which memories might help. The scaling of this particular thing is exponential. So because you start with one of your distillery units there, that's your mashing step, and then you must take two more, and then you must take two more. So you have a spatially exponential and temporally doubly exponential scaling for this process. Okay, so now, what happens if you use memories? Well, this turns out to give you quite a dramatic simplification of this distillation protocol, and indeed makes it possible to scale it. So the first thing you do is slightly adjust the protocol. So So you take a photon subtracted state, and instead of preparing two of them, you simply start adding it on to one you prepared earlier. So you don't have the additional resource of preparing two of these states, right? You start one, you take one you prepared earlier, so these two are now different. So that simplifies it somewhat. But the second simplification you make is to note that your memory acts like a beam splitter, and that this mode, output mode here, is then a matter mode, or alternatively the other mode is a matter mode. So you can put a memory in there which allows you to iterate this thing, storing the intermediate results, and that also gives you an increase in efficiency. So here's how you do it. You prepare a photon subtracted pair of states in a memory, because you can generate light matter entanglement in this memory, and then you can do, by way of putting weak pulses on, as I showed you earlier, you can use this as a little weak beam splitter, waiting to see whether you subtract a photon. Failed events leave the excitation in the memory, so you don't have to start over, and that's an origin of the scaling advantage. And then you mash these two states together, again using the memory as a beam splitter. And if you do this iteratively, you find that you can distill arbitrary amounts of entanglement with just 4 memories in a fixed spatial, set of resources. The state you get out is not exactly the same as you get out of the Brown protocol. It's not fully Gaussian, but it turns out to be just as effective for doing things like teleportation. So here's an example where even using low quality memories, in the sense of low efficiency memories, turns out to give you a dramatic advantage in networking. Okay, let me finish. I have, what, 5 minutes, is that right?
Yes.
Okay, so let me finish up then relatively quickly by changing directions in the direction of solid state. So I illustrated it, or asked the question at the beginning whether one could simplify these even further by trying to build them into solid state materials. And here's an example of a solid state material which is receiving quite a lot of attention for building quantum optical information processing devices, that is diamond. And there are many ways to do this. These gallium phosphide films built on diamond, photonic band gap crystals, various ring resonators and what have you. I stole this slide from Paul Barclay's website at Hewlett-Packard. But it illustrates the point that here is a material that's got some great promise. And a key thing that I would point out here is the scale. You probably can't see that one, but here you see that the scale of these devices on the order of microns. And that will turn out to be important for what I have to say later. Okay, so how would one build memories into this kind of material? Well, there are many ways to go. Nitrogen vacancy centers, for example, which people have shown have very long lifetimes if you map them into the nuclear spin. But here's another way to go, and that is to use the fact that the diamond is a very high-quality oscillator. So if you take the diamond structure, it looks like 2 interleaved cubic lattices. And these 2 interleaved lattices can actually oscillate against one another. And that is an optical phonon. Because diamond's an extraordinarily stiff material, this oscillation frequency is very high, about 40 terahertz. And the key thing about having such a high frequency mode is that at room temperature, the thermal occupancy of that mode is negligible, less than 1 part in 1,000. And more importantly, any surrounding bath is similarly got low occupancy. So the time scale for a single phonon from the bath to leak into this mode is long. I say long, I'll show you what I mean by that later. So here's the phonon dispersion map, here's the phonon frequency, here's the K vector in the 1, 1, 1 direction of diamond, and what we're looking at here is optical excitation of the LO phonon here. This has a very large Raman cross-section, which allows us to use it in the memory configuration shown here, where the metastable states are now the n=1 phonon excitation. And we can use light at around 800 nanometers or so, which is strongly detuned from the 4 eV conduction band in diamond. But because the cross-section, the Raman cross-section is very high, that still turns out to be a reasonably effective excitation mechanism. Now, once you've excited one of these vibrational modes, it will decay. And the mechanism by which it decays is this so-called Clemens channel. That is a spontaneous decay of the optical phonon into 2 acoustic phonons. And the time scale for that is on the order of 10 picoseconds. So this is, in some sense, going to be a really bad memory, because in 10 picoseconds, light is going to travel on the order of 300 microns or so. So if you're thinking of building a global network, you wouldn't use this as a memory. But if you look, remember what I said earlier, a nanophotonic processor in diamond, 300 microns is actually an awful lot of real estate. So it's not inconceivable, you know, if one wants to exuberate into the realm of some fantasy, that one could make use of that. So how does one do it? Well, very similar to what I just showed you for the cesium Raman memory. Here we take a piece of diamond, we send in a write pulse and a read pulse. So in that sense, things are very, very similar. The polarizations are shown there different than the Raman memory before, for technical reasons that I won't go into. The second thing to note is that what we're going to do here is slightly different before. What I showed you before was, here's a phonon, here's no phonon, here is, this would have been the control light, and this the quantum light. In fact, what we're going to do is reverse that situation now. So the control light is coming in here, which means that there's some probability that it will scatter a Stokes photon, and in that process will generate a single phonon. And the reason we do it that way is that it allows us to implement directly the DLCZ network protocol, quantum repeater protocol. So what we do then is we look over here for when this detector fires, because that detects the Stokes photon. And when we detect a Stokes photon, we infer that we must have had a phonon generated in the diamond. And to assess whether that assertion is correct, we come in now with a read pulse here, which is tuned over here, and we look for the anti-Stokes photon that arises when this control pulse scatters and pops that phonon back into the ground state. And we look for that anti-Stokes photon over here. So we're looking for the coincidence between a Stokes and an anti-Stokes photon. And if my hypothesis is correct, then every time we see a Stokes photon, we must see an anti-Stokes photon. Okay, so, of course, qua efficiencies and what have you, but there's well-known ways in quantum optics to take account of those, effectively to ignore them. And that is done by measuring this correlation function here, G2 Stokes anti-Stokes, which, for the purposes of what we want here, is the probability that we generate both a Stokes and an anti-Stokes, divided by the probability of Stokes alone and the probability of anti-Stokes alone. And one can bound that by classical fields. So here, if that quantity is greater than 2, that indicates that we've got non-classical correlations, that is, correlations that could not arise from simply random fields classical fields being associated with the Stokes light and the anti-Stokes light. So the place to look is this point here, around 0 delay. This point here at minus 12 nanoseconds, 12.5 nanoseconds, is simply the next pulse from the laser coming along. If you look here, what this says is what is the rate at which we get an anti-Stokes photon having detected a Stokes photon. Whereas this here is what is the rate at which we get a Stokes photon having detected an anti-Stokes photon, the reverse if you like. And you can see there's a great difference between these two, showing that that sequence, that model I told you, Stokes generated, leaves a phonon there, anti-Stokes is the readout, is palpably the right model for this. So what we see there is that we have got Stokes anti-Stokes correlations beyond the classical limit. So we're really able to generate these non-classical excitations in diamond. And if we're able to do that, we might ask the question whether we can go the rest of the way on the DLCZ protocol and take two diamonds and generate entanglement between them. And the way we do that is just to implement the DLCZ protocol, which is to take the possibility of Stokes photons from each of these detectors and erase the Witch path information, detect the Stokes photon here, and then to look for the anti-Stokes photon, again erasing the Witch path information, and detect that over there. So again, it's a similar kind of experiment, but here's the way to think about it. Take a beam splitter. If we put one photon in, we generate entanglement, path entanglement at the output. Either photon there, or both photon there, and photon here. So we have that path entangled state. If we were to take, forget the arrows should be going the other way. If we were to take an entangled state, 1, 0 plus 0, 1, and put it into this beam splitter, then for sure it will come out, the photon will come out this port. So unlike the usual random splitting of photons, if we put in this entangled state, then we get light out of one port, definitely. So here's how we apply that to the diamond. When we detect an anti-Stokes when we detect a Stokes photon out of this port of our beam splitter, we create a phonon which is delocalized or shared between these two diamonds, with a phase that is set by the phase difference of these two optical paths. If that phonon really is in a 1, 0 plus 0, 1 state, when we read it out, it will come out as a 1, 0 plus 0, 1 anti-Stokes photon, which means that for sure it will come out the same port as we receive the Stokes photon from. So that's what we're looking for. In this case, do we see the anti-Stokes photon coming out the same port as the Stokes photon? And by adjusting the phases in the anti-Stokes path, we can show that that is the case. So here is the detection of an anti-Stokes conditional on detection of a Stokes photon versus phase in the anti-Stokes path, and you can see that the fringes which illustrate this coherence and indicate therefore that there's the possibility of entanglement. And we can determine whether the state is entangled itself by measuring at least part of the density matrix of the anti-Stokes light. So here is the case where we get a Stokes photon but no anti-Stokes. Here is the sector where we get a Stokes photon and one anti-Stokes. And here is the sector where we get one Stokes and two anti-Stokes photons. So by taking this and setting these other elements that we can't easily measure to 0, we can get a lower bound to the entanglement. And that we do by way of the concurrence, and the concurrence turns out to be positive. With the statistics that we have, we can give a confidence that it's positive with 98% probability, and therefore we assess that there really is entanglement between these two diamonds. We can determine in the usual post-selected way what the character of the entangled state is, and we find that the fidelity to the nearest Bell state is around 0.9. Okay, so there it is. Photonic quantum memories can be robust, fast, and simple, and I illustrated that by showing you a quantum limited memory, Raman memory in room temperature cesium. Quantum memories don't have to be perfect to be useful, and I showed you that even with the performance of the memories that we currently have, building an efficient CV entanglement distillation network is plausible. And then finally, that there are approaches one may consider to building them in room temperature solids. I illustrated one in terms of using longitudinal optical phonons in diamond. And just to finish, make sure that you see who the quantum memory group are here. This is an old picture. Josh is still around. Klaus has moved on to ETH. KC is writing his thesis. Gina has a faculty position in Delaware, and Ben in Ottawa. So, good, thank you. Oh, and these guys are the people on the right, guys and girls who are on the left, who are the current people working on it. Thanks for your attention.
Thank you very much for this talk. Are there any questions?
Hi, Ian. How's it going? Yeah, really impressive talk. I'm very interested in distillation, especially when you have heavy constraints. I've been looking at that recently, though in the discrete case rather than the continuous variables. I have to admit I don't know the details of the scheme that you're talking about. What I was interested in is how robust that scheme is to the imperfections that come with, as it were, every round of the procedure that you apply. You mentioned that it can distill to an arbitrary level, but is there a way to characterize the susceptibility to the imperfections that you must introduce each time?
Yes, so in terms of the efficiency and fidelity, yes. I think we have not yet fully incorporated potential noise sources though, but Josh, you might have a view on that.
Yeah, no, actually, so we haven't looked at, we've looked at decoherence as essentially loss during the storage.
Okay.
And it's obviously the performance goes down the more decoherence there is, but it's this time bandwidth product thing. As long as that's much larger than the number of rounds that you need.
I mean, obviously the discrete case is been studied by a whole bunch of people, and you normally get basically a very clear limit to how well you can distill based on obviously how many errors you introduce at each level. Yeah. And clearly you can't distill to more than one round worth of errors.
Yeah. So and in the CB case, the upper limit for the amount of entanglement in the state is infinity. Yeah. And so you can't, if you keep distilling forever, you don't get to infinity. No. You get to something like in a standard protocol. It's essentially twice the squeezing parameter you started with. So you end up something like that.
Okay, sorry, I have to suppress this discussion. Maybe we can talk about it at coffee because we're running a little bit late. Are there any other questions?
Quick question.
Yeah?
So the tuning of 30 gigahertz allows you to have very broad kind of photons. So how does it fit with the down-converted photons? So I guess it's very nice that then suddenly you don't have to filter it much.
Yes, that's a very good point. The best sources so we have used in the past bulk sources in which we use a particular technique to get a narrowband photon which has got perfect timing with respect to a classical pump. The best we've seen on that is on the order of a nanometer, but John Rarity has used the same concept, and he has gotten down, I think, to about half a nanometer. So whether one can push that or not, we are exploring. But it certainly means that if you're building a cavity source, the constraints are much, much easier. And that's also something that we're looking at.
Okay, I have one last speculative question. Actually, you said the coherence time in the diamond was limited by the decay from the optical phonon to two acoustic phonons.
Yeah.
Is there any way, is it conceivable at all to structure the diamond at a level where you can suppress the modes of the acoustic phonons to preserve the coherence for a little bit?
I think that's a very good question, Michael. We had a coffee and beer fueled discussion with Steve Prower about this, in which we came up with a perfect scheme to do it. You build a phononic band gap.
Yeah.
And then, as the effects of the drugs wear off, you realise that in order to do that, what you have to do for these photons is you have to have a pure carbon-12, carbon-13 lattice, where you put down exactly 2 unit cells, and then another 2 unit cells, and then you have to do that in 3 dimensions. So in principle, it's a brilliant way to do it, but I think the practical aspect of doing it would be still quite a challenge.
Okay. Well, thank you very much.